Uh, we have defined the continuity using the convergence of a sequence. Remember, for a map defined on A and take a value in another Euclidean space Rn, where A is a subset of Rn, then we said f continuous at a point belongs to the domain of definition A. If by definition, this continuous means that whenever xk is a sequence contained in the domain of definition and the xk converges to A, we will have the value of f along this sequence, which is a new sequence in Rn, will converge to fa. If a function f defined on A take value in Rn has this property, it maps convergent sequence to convergent sequence, then we said f is continuous at this point. So this is very convenient, but we for the later need, we also give an equivalent description of continuity. Okay, this theorem. Consider this map or this function. Here function will mean vector valued functions. F from A to Rn. We said that this function is continuous at a point in its domain of definition, little a. If and only if the following statement is true. For any epsilon positive, there is a delta positive such that the distance from fx to fa less than epsilon holds for any x. Of course, this x need to be in A. Otherwise, fx will not make sense, and very close to the point A, which means x also need to in the delta neighborhood of A. So this is a very useful description of continuity. Okay, so this description means what? It means exactly the image of, maybe I will, the image of f, no, the image of A, the image of the intersection of A and the delta neighborhood of A is contained in the epsilon neighborhood of fa. So this is very convenient and a very brief description of continuity. So this is sufficient and a necessary condition for the continuity of a function. Okay. And what this means? This means that whenever x is close to A enough, the image of x, that is fx, will be arbitrarily close to fa. As close as we want, as close to fa. As we want. That is, given any epsilon, you want how close fx to fa. How close the distance, how small the distance from fx to fa you want. This can be true provided x is close to a enough. That is x. That is to say, the distance from x to a is small enough, less than delta. So this is why we write fx belongs to the delta neighborhood of a. Okay. So the proof of this theorem is a very typical application of the definition using sequence. Okay. So the proof of this theorem, this is a two-way verification. Firstly, we want to prove this direction. That is, f is continuous at a. We want to show for any epsilon positive, we want to find a delta positive such that if x belongs to a and the distance from x to a is less than delta, then the distance from fx to fa will less than epsilon. Okay, so this is an equivalent description where we wrote in the theorem that x belongs to a intersect the delta neighborhood of a. This means the same thing. Okay. Now, how to get this delta? So we argue by contradiction. If this is not true, if there is no such a delta, then there is an epsilon positive, so that any delta could not satisfy our requirement. Okay, so there is an epsilon positive such that for any delta positive, this is always not true. This is not true means that there will exist an x belongs to a, and the distance from x to a, although the distance from x to a is less than delta, but the distance from fx to fa will not less than this epsilon. So the logic is here. We want to prove that for any epsilon, there is a delta has the following properties. So the opposite fact of this is that there is an epsilon, so that any delta could not satisfy our requirement. So this is the typical idea of arguing by contradiction. So if our desired result is not true, we will have these properties. We can find an epsilon positive, so that any delta could not satisfy what we want. Therefore, it satisfied another the opposite side. Okay. So since this delta is arbitrary, we can take delta to be 1, 1/2, 3/2, 1 over k for every k. So the x declare the x here depend on delta. For different delta, the x will be different. So for any delta, you will have an x. So for delta equal to denote the x corresponding to delta equal 1 over k by xk. Then xk of course belongs to a, and the distance from xk to a is less than delta, which is 1 over k, but fxk, the distance from fxk to fa will not less than epsilon. Okay, so this implies that xk converges to a. Because the distance sk goes to infinity, the distance goes to 0. Therefore, xk converges to a. On the other hand, this means that the image sequence fxk is not converged to fa. So this is a contradiction to the continuity of f at a. Because by the continuity of f at a, whenever xk converges to a, fxk should converge to fa. But our argument shows that if our desired result is not true, then we can find a sequence converge to a, but the image of the sequence does not converge to fa. Okay, so this proves the only if part of our theorem. That is to say, from the continuity of f, we can get for any epsilon we can have such a delta positive. Okay. Now we prove the if part. The if part is easy. We want to prove f continuous at a. How to prove this? We can only verify the continuity of f by definition until now. So to prove that f is continuous at a, we take a sequence xk in a, and the xk converges to the point a. We want to show fxk converges to fa. This is what we want. Once we can prove that fxk converges to fa, then f is continuous. Okay. So for this purpose, for any epsilon positive, by the conditions of the theorem, there exists a delta positive such that x belongs to a, and the distance from x to a is less than delta. Together will implies that fx, the distance from fx to fa is less than epsilon. Okay, this is the condition of the if part of the theorem. So, with this in hand, because xk converges to a, so for this delta, there exists a capital K, a natural number capital K, such that if the index k is not less than capital K, then the distance from xk to a will less than delta. And also note that our xk is a sequence from a, therefore xk is a point in a. For every index k, this is true. For every index k not less than capital K, this is true. This two fact is true. Fxk, the distance from xk to a is less than delta, and xk belongs to a. Okay, but by the above condition here, this is the condition assumed by the if part of the theorem. By this condition, because our xk verified this condition, verify the requirement of this condition for x, we will have, maybe we denoted this by start. So by our condition start, we have fxk, the distance from fxk to fa will less than epsilon. So in conclusion, for any epsilon positive, we can find a capital K. Whenever the index K is not less than capital K, the distance from fxk to fa will less than delta. This means the distance from fxk to fa, this means that, yes, the distance from fxk to fa goes to 0, right? Therefore, fxk converges to fa. So this is proved. fxk converges to fa.